Welcome to our session, Outsmarting Smart Contracts. My name is Ashkenazy, currently VP Product at Cyber. With me here today, my colleague, Shahar Zini, who is hiding over there. So before we begin, the basic slides of who we are and what this session really is about. So our background is really in the offensive cybersecurity space. This is kind of where we grew up and where our state of mind was shaped when it comes to being critical thinkers in security. We spent many years working together in the government of Israel, and that's all I can say. So in the past 2.5 years, we've been designing and developing an automated red team machine at Cyber, basically building a virtual hacker that helps you. It's not an offensive tool. It helps you find gaps in your security and fix them. And we're also trusted security advisors. And what I mean by that is that we get to basically talk to a lot of people about all kinds of problems they have in cybersecurity, hopefully give them some solid recommendations, but mainly for this session, we get to hear a lot about new trends, new technologies, new hypes that are out there. Now, we're also huge fans of the marketing engineering divide, and what I mean by that is that we're really excited every time we hear about this new amazing product that can fix everything, right? It's 100% secure. It not only fixes problems of the past, but it also fixes problems of the future that you've never even encountered and you cannot articulate. And every time we hear something like that, we get goosebumps when we have this urge to learn more, research, and hopefully find some flaws in this otherwise perfect technology. So what do you think about smart contracts? This is a question we get asked a lot, and probably because we engage a lot with the financial services industry. And all of them are thinking of blockchain or smart contracts or either piloting that already. And they've also kind of a hype victim. And the follow-up question I usually get asked is, so is it 100% secure because it is encrypted? Like the blockchain, it cannot be tampered with? So the short answer is no. But this session is really, and as you've seen, we're not crypto gurus of any kind. We are offensive cybersecurity professionals with a specific state of mind in a journey to learn about smart contracts. And the session is really about our journey and about what we think about trust in the world of smart contracts. So this session, a word of warning, this session is technical. About 60% will be code samples. 40% will be high-level fluff, like what I'm doing right now. If you're not into technical stuff, this is your chance to escape. I won't hold this against you. If you choose to stay, we're going to talk about smart contract basics, really just scratching the surface. We don't have time for a full premiere. We're going to talk about old world trust, new world being the brave new world of smart contracts, and we're going to look at 2 technical examples. Finally, we'll talk about what the future may hold and how this field could evolve. Now, a couple of disclaimers. There's a whole technological stack and theoretical stack when it comes to smart contracts. We're really looking just at the layer of the smart contracts themselves, an inch to the left, an inch to the right, the other way around, your other right, and that's it. And also we'll be focusing on the Ethereum blockchain and the kind of the pure concept of smart contracts as it was originally conceived, and all kinds of hybrids that have evolved over time. All right, so what do you need to know at the very basic level about smart contracts? So first of all, smart contracts are really just transactions on a blockchain that contain code that you can potentially invoke and also a state. They're commonly written using Solidity, not necessarily, but commonly using Solidity. It's a high-level language, and if you've ever developed in JavaScript or C or something of that nature, it will take you 5 minutes probably to jump right into that and write your first smart contract. The technology stack that runs all this stuff is wonderful, but it's also kind of new. And like any new stack, it is a bit naive. And finally, the only thing left for us to know is that once deployed, a smart contract is publicly accessible, like any transaction on the blockchain, and is immutable. It cannot change. Now, the state of the contract can change, but the transaction itself cannot. So as I said, trust is going to be the main theme or a recurring theme in this session. But what is trust anyway? So most of us can probably articulate what they think trust is, and I don't remember the exact formal definition, but it's something along the lines of a firm belief in the truthfulness of something or someone. And just by looking at you as an audience, I can see that you have an immense level of trust in society. And the reason I say that is that I see no swords, no goats, no sheep, and no materials to make a tent or any kind of shelter. You trust your environment, you trust society to provide you with these things in exchange for some kind of abstract concept of money. But let's look at transactions, because trusting transactions is more aligned with the blockchain and smart contracts. So what is the most important transaction we have in our lifetime? Anyone? The single most important transaction that we do? None of you is married? All right, so I didn't think about this example, unfortunately, a few days ago. So I'll stick with the example I had in mind then, and this is the second most important transaction, and that is probably buying a house. Highly risky transaction, involves a lot of money, and in the old world, there are tons of trust mechanisms at play that help us make this very important decision. So first of all, we employ what I call our personal security controls. Our knowledge, our experience, our intuition, our prejudice even, knowledge from our family and friends, and maybe even we pay for some professionals to help us out. And then there's the financial services institutions that are in charge of actually making this transaction happen, and we trust, if to oversimplify this, at the very least we trust our bank to let us know, to send the money to the right place and then let us know if something bad happens. If that fails, some of us trust the government. The government will help us, right? With law enforcement, hopefully in agencies and things of that nature, even if it's a cross-border thing. And finally, none of us trust insurance companies, but we just hope we can coerce them to pay us if all else fails, right? So there's a whole mechanism here that has been evolving for hundreds and thousands of years. It's kind of the basis for trust in human society. This beauty right here is the concept of smart contracts, trust in smart contracts. In code, we trust. This is it. Now, I get it. I really do get it, and I actually love it, and with one hat that I'm wearing, which is the geek hat. I've been a geek my entire life, and as a geek, just looking at this, understanding the amount of inefficiency that is cut away by trusting just the code, that's awesome. No more banks, no more mediators, no more authorities, no more lawyers to cut their fees. Just code, pure and simple. Unfortunately, I also have a few other hats, and I'm going to wear two of them now, which is maybe a bit awkward, but I have a software engineering hat and I have a security practitioner hat. And with these hats on, I know a few things. I know that I've seen systems that have been hardened by fire for 40 years or more, have been, anything and everything in the world has been thrown at them, but they're still vulnerable. They're less vulnerable, but they're still vulnerable. Which is why, for me, it's kind of hard to accept this as the only layer of protection that I have. So I'd like to invite my colleague, Zini, now to start with the first example, and I will be back for the second technical example to talk about trust.
Thank you, Adi. So we have established the fact that the security of smart contracts is based on our ability to trust and verify code. However, that is sometimes easier said than done. In the next example, we're going to see how the ecosystem is so complex that it is sometimes very tricky to write secure code. So let's take it from someone who knows. I trust no one, not even myself. Who do you think owns that quote? Nobody? Well, it is Stalin, and he knows a thing or two about trust, right? So in order to surface some of the complexities of the platform, let's imagine and position ourselves as experienced software developers that are taking our first footsteps in this amazing world of smart contracts. And we came out with this innovative new idea of building an eBay-like platform on top of the Ethereum network. We're going to call it CryptoBay. Very creative. So CryptoBay will have all of the main functionalities that you would expect from an eBay-like platform. So sellers can list their products, and then buyers can bid on those products by sending their funds to be held in escrow, and then those sellers can either reject or accept those bids. Now, we are going to see how even minor bugs in CryptoBay, combined with the unexpected behavior of the platform, can lead to disaster. Now, we are going to pinpoint some very specific issues. However, they are not the main concern. The bigger problem is that the platform and ecosystem as a whole are riddled with all kinds of issues with unexpected behavior. And you really must be extremely experienced to be familiar with all of those quirks. In the same sense, CryptoBay is just an example. It's an example of a small-scale, simple project being developed by security-aware developers that can still have some unexpected behavior. So let's see how we can, let's say, sensibly implement CryptoBay. So we were told that it is best to limit the amount of new code we introduce and to always use verified libraries whenever we can. So we'll do just that. We'll start by having our CryptoBay contract extend and build upon a verified implementation of the ERC-223 protocol, which basically is an evolution of ERC-20. Now, by doing so, we are going to have our very own secondary token that will be used to do business on our platform. We're going to call it CryptoBay token. Again, very creative. Now, by using verified library, we are reducing the risk of having a major security issue because that code has already been tested, verified, and audited. We also know that we'll need to store some information about the different products. So we'll define the product record struct, and it will store information about the seller of the product, the name of the product, and a list of bids. And a bid is just another simple struct, and it has information about the buyer, the amount of the bid, and a flag indicating whether or not this bid has been canceled. We will also keep a counter so that we can allocate product IDs sequentially, and a mapping between those product IDs and those product records. So now let's say that I am an amateur lockpicker, and I've just acquired myself my brand new lockpicking kit, and I want to sell my old one on CryptoBay. So I will call the sell product function, and I will specify that I want to sell a lockpick. Now, sell product function will do two things for me. First, it will allocate a new product ID, and then it will fill in the necessary information about me, the seller, and the product that I'm selling. Now, on the right-hand side of the slide, you can see the memory map of CryptoMap after we have called that function. So there's 0 over there on the middle, which is the product ID, because that is the first ever product on CryptoBay. And it points toward the product record, which has information about me, the seller, the name of the product, lockpick, and a pointer to an empty list of bids. Now, Jack has seen my product on offer, and he would like to bid 100 tokens for my lockpicking kit. So Jack will have to follow these 3 steps. First, he will have to acquire some CryptoBay tokens, right? Then he will need to transfer those tokens to be held in escrow. And lastly, he will need to add that bid information onto the list of bids for that product. So Jack will start by calling the buy tokens function, and he will pass in some ether, and he will receive some CryptoBay tokens under his name in return. Then he will call the bid on product. He will specify product ID 0, amount is 100, and then that will call the hold fund in escrow, which will transfer 100 tokens from Jack's account onto CryptoBay's account, effectively holding it in escrow. Lastly, he will allocate a new bid record. He will fill in the information and will push it onto the list of bids for our product. So again, on the right, we can see the memory map of CryptoBay, sorry. And basically, you can see the first bid is of Jack's, but there are 2 other bids. So we have another bid for 150 tokens and another bid for 200. Now I, as the seller, have now noticed that I have 3 different bids for my product. And being Israeli, if I get an offer for 200 tokens for my lockpicking kit, I will not accept 100 tokens. So I'm going to reject Jack's bid. To do so, I have to do 2 things. First, I will need to refund Jack's tokens back, and then I will need to get rid of the bid information Jack inserted onto the list of bids. So I will call the reject bid function, which will call refund bid, and refund bid will take 100 tokens back from CryptoBay's account onto Jack's account, effectively refunding him. Then, in order to remove the Jack's bid information from the list of bids in a gas-efficient manner, and this is something that is unique to the Ethereum platform, we need to use some kind of a trick. So what we're going to do is we're going to overwrite Jack's bid information with the information from the last element of the array. So we're going to take the last element and copy it over the first one, which is Jack's bid. And then we're going to decrease the size of the array by 1, and therefore eliminate the last element of the array. So we are left with all of the bids but Jack's. Now, I would expect that such a small-scale, simple project to be very easy to implement and implement securely. However, I can now reveal to you that the very few lines of code that we have just seen contains a minor bug. And that minor bug, combined with the unexpected behavior of the platform, we can now escalate that bug in order to be able to steal money off of CryptoBay. And we're going to see how. So we're going to chain together a couple of different bugs and features in order to have a full working exploit. Now, the first piece of the puzzle is, I would say, an interesting flavor of the reentrancy exploitation technique. And the problem lies with the highlighted line in the middle. Now, some of you are probably familiar with reentrancy bugs, and some of you probably never heard of that. But don't worry, that's OK. We are going to step this through. So let's now assume that we are malicious actors, and we're trying to steal money off of CryptoBay and abuse CryptoBay. So we will be trying to find things that the original developer did not consider. Now, one of the features of Ethereum is that there are two types of entities. There are wallets, and there are contracts. And surprisingly enough, contracts can have transactions and can own tokens. Now, according to the ERC-223 protocol, and by the way, this is not unique to ERC-223. Basically, every evolution of ERC-20 will do that. Whenever we transfer tokens into the address of a contract, we must call a callback function on that contract. And basically, this is just to avoid situations where tokens were transferred to a contract that did not know how to handle them. So what we can do now as malicious actors is we can either, let's say, bid on a product using our wallet, but that's kind of boring, or we can do so using a contract that we create, and that gives us the opportunity to disrupt the normal logical flow of CryptoBay. So let's see how that works. So let's start by setting the stage. So I have created a product, and then I have created a contract to bid on that product, and now I'm rejecting that bid. So we have one product, one bid, we're now rejecting it, and all of that belongs to me. So I have called reject bid function, which we'll call refund bid, which will try to refund my money back. So it will try to transfer some amount of tokens back from CryptoBay's account onto my account. Now, my account is an address of a contract, because we have used the contract to bid on that product, which means that now, according to the ERC-223 protocol, we need to call a callback function. And the thing is that that callback function is under my full control. So I can write whatever code I want within it. And one of the interesting things I can do is I can call reject bid once more, like so. Now, that will be the classical way to exploit a reentrancy bug. Now, let's just assume for one moment that the last two lines of refund bid were reversed. So we would first transfer the tokens, and only then we would mark the bid as canceled. If this was the case, then we will go from reject bid to refund bid. We will then transfer some more tokens. We will call the callback function once more, and then the callback function will call reject bid. And we can basically continue doing this cycle until we empty out CryptoBay out of all of its tokens. However, we are security-aware developers, and we have lived on this planet for long enough to be aware of reentrancy bugs, and we have followed the best practices as to how to avoid them. So we first cancel the bid, and only then we transfer the token. So we should be protected. Now let's trace what happens next. So we call reject bid, which we'll call refund bid, and then we'll hit that if statement over there. And because that bid has already been canceled, that if statement is going to fail, and we are indeed protected against the classical way to exploit a reentrancy bug. However, when I now unwind the stack, I will hit that highlighted line for the first time. So this will be the first time that I will reduce the size of the array by 1. Then, if I unwind the stack some more, we'll go back to my bad contract, the callback function, and refund bid and reject bid. And soon enough, we will hit the highlighted line for the second time. So we will actually reduce the size of the array twice instead of once. Obviously, that's a bug. However, I would argue that that's a minor bug. Nevertheless, we are going to see how we can actually take this bug, and little tiny minor bug, I would say, and we can escalate it into being able to overwrite critical data structures of CryptoBay. And specifically, we are going to overwrite the piece of information that says how many tokens we own. Okay? Now, in order to see that, we're going to take a look at a totally different piece of code. It's unrelated to CryptoBay in any form. And this contract is called Unlimited Array Exploit. And it has two variables, a flag and a dynamically sized array. Now, every contract in Ethereum has its own private warehouse where it stores information that should persist across different transactions. So, for example, for CryptoBay, we're going to have all of the data that regarding the products and the bids is going to be stored there, but also the balances of each user. So how many tokens each user owns is going to be stored there. So this warehouse is built using slots. And each slot can hold a 256-bit number, and it is labeled using a 256-bit number. And so basically, it's a mapping between 256 bits and 256 bits. You can also, it's sometimes easier to think of that as a very large array starting from 0 going all the way to 2 in the power of 256. The important thing to note here is that this warehouse or storage stores all of the important information that the contract has. So the amount of tokens that I own is stored within some slot of that storage. It's like the memory space of the contract. What Solidity does is it will allocate each of those variables onto the storage in a sequential manner. So it will allocate the flag variable to slot number 0, and then the array to slot number 1. However, because this is a dynamically sized array, Solidity does not know in advance how many elements are going to be stored there. So it can't pre-allocate them. So what it does is as follows. It will store at slot number 1 only the length of the array, and will store all of the data items in a totally different location. And that location is calculated by calculating the SHA-3 hash value of the position of the array. Okay, so if the position of the array is 1, then we will calculate the SHA-3 of 1, which is just another number. Right? So let's say that I'll push the number 147 lit onto the array. So it will be stored at slot number SHA-3 of 1. Then if I'll push another value in, it will be stored at SHA-3 of 1 plus 1. If I'll push another one, you guessed it, SHA-3 of 1 plus 2. If I remove those 3 elements and I push 200 times the number 1, then we're going to have a continuous block going all the way from SHA-3 of 1 to SHA-3 of 1 plus 199, all filled with 1s. Then if I want to write 1337 onto index number 100 of the array, then it will be placed at SHA-3 of 1 plus 100, right? Which means that we can now deduct a simple formula. If we want to write to index x of the array, we should write it to slot number SHA-3 of 1 plus x. Keep that in mind. Now, I want us to take a look at an interesting phenomenon. So let's say we're starting fresh. We have a fresh new contract. The array is empty, so its length is 0. And now we'll start by decreasing the size of the array by 1. What do you think will happen? Should it throw an exception? Should it fail? Should it succeed? Well, apparently, for some reason, Solidity treats the length variable as just another unsigned variable. Unsigned variable. Which means that if I decrease the size of the array by 1, we can now underflow it, and it becomes 2 in the power of 256 minus 1. So this is a very large number that does not even fit on the slide, right? So this is what we call an unlimited array, because that array now can access 2 in the power of 256 minus 1 different elements. And if we think of that, when we last exploited the reentrancy bug, what we were able to achieve is that we were able to reduce the size of the array twice instead of once. So we started with an array of bids containing just 1 element, and then we hit the line, the highlighted line for the first time. So the size of the array was reduced to 0, and then we reduced it again, and basically it became an unlimited array. And now the fun can begin. Because now I can do something like that. So I want to write 1337 again onto index number 4EF1, whatever this large number is, right? So we go back, and according to our simple formula from just a minute ago, we should place it in slot number SHA-3 of 1 plus the index, which is SHA-3 of 1 plus 4E, whatever. The thing is that the labels for those slots are also 256-bit number, and they can be overflowed. So I have carefully selected that number so that that calculation overflows and yields 0, which means that we will now write 1237 onto slot number 0. But that is exactly the same slot where we allocated flag into. So now if I call the getFlag function, which retrieves the flag, we will get 1337. Which means that by having this unlimited array, we can now have an out-of-bounds write and write into any slot of our choosing within the memory space of the contract that holds all of the important information of the contract. And we don't have ASLR. It's irrelevant. Everything is public. I don't need to shape the heap or anything. Everything is public, and everything is known. So we have seen how we can use the reentrancy bug in order to create an unlimited array, and we have seen how we can abuse an unlimited array. The only missing piece that we need is a gadget that allows us to write meaningful data onto an index of the array that we can control. So we overwrite something of a meaning to us. So there are a couple of those within crypto-based code, but we'll take a look at one that uses the function that we have already become familiar with, so reject bid and refund bid. And basically, the reject bid function is a public function. So I can call it with whatever parameters I want to. And therefore, I can fully control the bid ID parameter. Then on the highlighted line, we calculate a pointer to the storage based on that bid ID. So if I fully control the index to the array, then I can, let's say, almost fully control the pointer. Then we pass on that pointer to refund bid, and we write true, or 1 in computer language, to some location of the storage. And because of the way the bid struct is defined, we can actually overwrite the higher 128 bits of any slot in the memory of our choosing. So we can choose, for example, the slot that holds information about how many tokens I own, and I can overwrite the higher bits, and then I can basically gain 2 in the power of 128 new tokens. Awesome. So let's recap the entire exploitation flow. So we start by creating a product, which gives me access to the seller functions. Then we bid on that product using a contract that we create. Next, we reject that same bid. Therefore, we trigger the reentrancy bug, and we turn the bid array into an unlimited array. And then we call reject bid once more with a carefully calculated bid ID so that we will overwrite the higher bits of the slot that holds the information of how many tokens we own. Okay? So we are going to see a short demo of how that works. And basically, we are going to create 2 different contracts. One is a CryptoBay, of course, and the other one is an exploiter, which basically automates all of that process for us so we don't have to calculate SHA-3s in the mind. So we start by creating a CryptoBay instance. And then we'll create the exploiter. We'll give it the address of the CryptoBay as parameter. And then we'll hit the exploit button. We'll wait for a couple of seconds. And then we're going to check our balance. So we're going to check how many tokens CryptoBay now thinks we own. And voila. We have a lot of tokens, right? So I don't know how this number is called, but I will call it gazillion, which means that I'm now crypto gazillionaire, and I can retire and give back the clicker to Adi.
Thank you, my gazillionaire friend. You can rest on your laurels. So really, we've seen now an example of really how hard it is to follow even simple code that you write yourself, how it can be exploited eventually. And in the second example, we'll be talking about trusting other people's code. And this probably is something most of us will be doing most of the time, using other people's code. And we'll be doing that with a rather simple example. It's going to be way shorter than the previous example. I'm going to use a simple game called Guess the Number. So in this game, let's assume that I'm the house. I'm now thinking of a secret number. Hopefully, you cannot guess it. And I can ask you to participate and guess the number. In order to participate, though, you would have to pay me 1 ether. If you're successful, I will give you the entire jackpot. I'm starting with 20 ethers. Now, it's not a super exciting game, but will help us understand a few concepts. So this is the meat of the contract, really. So we only have 2 functions here. As you understand, this is really a very, very simple game. And we'll start with the function guess. So you can invoke guess with an unsigned int n, which is your guess. And as a smart contract, I will just make sure that you indeed sent me 1 ether, and I will make sure that your number is in range. I will calculate P, which is the jackpot, and then I will call check and transfer prize, which again is a super simple function. The only thing it does is check that n equals a secret number. If they're indeed equal, I will transfer you the jackpot, the prize, and if not, you'll just get an event that you've made an incorrect guess. Super simple, super straightforward, yet has a very, very, very deep problem. So the one thing that wasn't on screen in the code, is the declaration of the variable secret number. Secret number is a private variable, but for those of you who've actually read the documentation, and not all people read the documentation, it could be confusing, private numbers are actually not that private. They're private only in the sense of modification. You can modify them, but you can definitely read them. And in order to read them, you don't need any kind of special powers or any exploitation. This is actually a feature of the blockchain. So we took this game and we showed this to a bunch of our friends, and of course they called us idiots, and they said we can just take your money easily. And we saw, this is just the kind of friends we have. So we saw two kind of schools of thought, I would say. One said, I don't even have to extract the number. I can just brute force the damn thing. You have a flaw by paying me the entire jackpot with my guesses, so I'll just try 11 guesses. That's actually not a great idea, because someone else could intervene in the middle, and while you're brute forcing it, take your money away. The other group, the better group, said, I'll extract the number and I'll just guess that number and take your money away. Very simple, and let's do that. So this is us naive guys, creating this contract with a jackpot of 20 ether and a secret number of 2, which we think no one knows. And this is our friends, guessing the number, which easy, should be 2. They've extracted the number, they've checked it. And this is the output. You've made an incorrect guess. Now, I'm going back to the issue of trust and the way we have shown our friends the code. Was just sent them the solution file, the solve files, the solidity files. And then they said, maybe you tricked us. Maybe that's not, the real files. So one thing you can do, you can use something like Etherscan. Etherscan is a block explorer, and one of the very, very nice features it has is code verification. Again, that's the only thing we have, right? We have to trust the code. So with this feature, as a smart contract author, what I can do is upload my code to the website and say, this code belongs to that address. Now, they don't take my word for it. All world trust, right? They don't trust me, and they compile the code that I've submitted, and they compare it to the code that's actually on the blockchain. If they match, I get this exact 100% verified, exact match. So this was kind of a frustrating moment for our friends, because this is 100% verified that this is the code, and they looked at it again and again and lost more and more money trying to get hard jackpot. But I can tell you right now that this game is not winnable. And the reason it's not winnable is that we have abused their trust in the code. So maybe some of you have noticed, maybe some didn't, but let's have a look at this. This is us typing the code, the problematic line, and it gets awkward just about now. Something really weird is going on. And I'll give you a hint to those of you who haven't realized yet what's going on. We're originally from Israel, and we read and write in Hebrew. Hebrew is a right-to-left language. So for us, one of the most natural things to check is how any news technology stack treats right-to-left characters, and if that can be abused. And one of the things we did here is we looked at things that worked in the old world, the world outside of smart contracts, and this was a nice trick and abuse that worked in high-profile attacks, nation-state attacks in the past, and it works as follows. Generally speaking, you would send someone a file called, for example, execute_invoice.pdf. This is what the file would look like to that individual. But once they click it, they're actually executing a file called something.exe. And the reason is that there's a right-to-left character somewhere in that string. But in the old world, there's some kind of mitigations. There's there's gateways, and there's the operating system, and there's endpoint protection, and there's always a responsible adult somewhere in the room. So let's close the loop here, and we'll get back to that issue. So when we were calling check and transfer prize, what you see when you look at the code that I send you, the code on Etherscan, you see the top line. You see the prize, PNN, and now you realize why we have so many remarks. It's just to make this feasible. But the actual line of code is N and P. So we've completely reversed the logic of the contract just by using this simple trick. And again, the fact that the only thing you have to trust is the code itself. So when we call check and transfer prize, the actual comparison is not your guess on the secret number. It's the secret number and the prize, both of which are under our control. So you can try and win this as long as you want. You will not be successful. Now, of course, this is just an innocuous, simple example. But what if this kind of trick and abuse is used in a very high-value contract in a function that only the owner can call whenever he wants? This can become devastating in that type of contract. However, and by the way, we haven't seen anything in the wild like this. We haven't seen anyone using this or doing this. As far as we know, this is presented for the first time. But that is not actually the real issue here. The issue is the process we went through as offensive cyber practitioners when we were looking at this potential abuse. We were having lunch, we were kind of tired, so we had some coffee, and we sat down and we just made a list of things that were kind of well in the world outside of smart contracts, and thinking maybe in a new naive technology stack, they just didn't have the time to treat those kind of things. And maybe if, again, the only thing you have to trust is code and you have very little security controls, this will be potentially devastating. And it took us less than 1 hour to come up with this working POC. And the only question I have is how many more are out there, and other people may not want to present this at RSA, they might want to actually use this to steal a lot of people's money. So what can we expect in the future? And by the way, this is the time to say that generally speaking, I think it's a wonderful technology, and I have a tremendous amount of respect to the people who have built this technology. It's just a very natural thing for any new technology stack out there, and we should just be expecting it. So a few things that could be improved, out of potentially thousands, but a few things that are close to our hearts. First of all is security by design or safety by design, and I know this is a term that gets thrown out a lot, but I have something really specific in mind here. So a lot of the applications in smart contracts are going to be repeating. It's going to be the same things. A lot of people will be wanting using voting for real estate transactions and all kinds of things like that. So the community needs to supply lots and lots and lots of reference implementations that have been tested by the best experts that are out there. There is no reason to rewrite lots of the code in these applications. Also, I would expect to have a subset of the language, which is safer. And you know how engineers are. They like to provide you with lots of features and over-engineer them and give you the most flexible language possible, which they did with Solidity. But maybe I'm willing to go for something less. I'm willing to trade some of this flexibility for a more secure language. For example, one that does not have underflows and overflows. I don't need it in many applications. In terms of development and validation, I've shown you an example of a problem with validation. And I don't know how many of you actually develop in Solidity and debug, like step into code in Remix, for example. It's really a pain, and there's a lot to be desired there, and we're only human. If something is really hard to do, we just avoid it. So this part really has to mature and fast. Now, patching is really the part where I clash head-on with the religion, with the ideology, if you will. And I'm very adamant about this. I think that you cannot have a static system in the dynamic world which is secure. It just doesn't work in my world. I've never seen anything like that works. And the proof, I think, is reality. People who have been implementing smart contracts, at least in the last couple of years, have been using all kinds of workarounds, proxy contracts and things of that nature, to make sure that they can patch if the need arises. And people have been trusting them to do so. And I think this needs to be formalized. And finally, there's third-party auditing. Again, something that you can do today, but it is not formal. I'm trying to borrow ideas from the world of old world trust. And for example, if I told you that a smart contract was audited by top 3 teams of security in the world, and you can verify that automatically. They've signed the contract saying, we verified that, we audited those functions at that date, that would definitely raise my level of trust in that piece of code. So what can we do now? So if you're a smart contract author, the first piece of advice I have for you is that for anything of value, use experienced developers. Juniors are just too expensive, if you know what I mean. One mistake can be devastating. Now, developers are great at building stuff. They're not so great at testing their own thesis. You need someone else. You need security professionals who are good at breaking stuff. So you need both, again, for anything of value. Use standards wherever you can. Strive for minimal code. Don't reinvent the wheel. Use other people's implementations if they're better and more experienced than you in the platform. And harness the security community with bug bounties. Now, you cannot be stingy about it. Good security professionals, fortunately for all of us probably, are well paid today. And I have seen bug bounties that offer between $5 to $25 per bug. This is ridiculous, and you might as well not do it at all. Now, also, patch enable your smart contract. Again, using the workarounds today, that's the best you have, and it's definitely better than not being able to evolve your code at all. Now, if you're a smart contract user, unfortunately, I don't have a lot for you. I would just offer you to use the same kind of trust logic you have in the real world. Like, would you pay a total stranger $1 million because he promises you he has the next new thing and, you know, he's going to make you a millionaire? Well, apparently some people do. And it's infinitely stupid in my mind, and people should not be doing that. So you need, again, to borrow ideas from the regular or old world of trust and only work with people you trust, de-anonymize the people behind the contracts if you're going to invest significant amounts of money. In any way, you're going to have to assume high risk because this technology, like it or not, is still new. There's still going to be exploits. You're still going to get burnt. So don't risk anything you're not willing to lose. And I will leave you with the very wise words of the genius Quentin Tarantino about rebuilding trust once it has been lost. I'd like to thank you for being with us today in this session. And I'd like to thank my colleague, Zini, who has a Category 5 stage fright for challenging himself and being here today. Thank you.
Thank you.